Good morning, class, or good afternoon, class. This is Mr. Gray, your online Advanced Functions MHF4U teacher. I just want to conclude, take a few moments and conclude Unit 1, the discussion on advanced polynomial functions, with a pretty typical question, and one that you may have done, certainly, but maybe wanted to just discuss and sort of piece together, see if we can bring everything together in this particular section or unit. And see if we can finish off the particular unit with a graphing and discussing the characteristics of a question like this. So let's start. If you're asked to graph and discuss the characteristics of a particular function, in this case it's a cubic function, we attack it by simply just looking at the original function on its own. We should be able to, at this stage of the game, recognize the fact that we have a leading coefficient, a equals 1, and this is positive. The degree of the polynomial function is n equals 3, so it's a cubic. And it's going to follow the basic path of a cubic. Now, from earlier, the basic path of a cubic looks like this. So that's going to be the basic look and feel of our graph. Now, our original function, f of x, given in the question, also gives us a whole lot of other clues, or at least a few more clues. We can identify Y-intercept, right? That's when x equals 0. When x equals 0, clearly y equals -6, or if you like, let's f at x equals -6. So there's a point on our graph. So far, so good. We also know from work in this particular unit, that the domain any cubic, as x is an element of the real number system. It's it's interval notation. If you like set notation, that's spanning between the domain spans between negative infinity and positive infinity. And similarly, the range for a cubic is the same. What else do we know? And behavior. All pieces of information that we discussed in this particular unit. As x approaches infinity, our cubic function approaches negative infinity. And as x approaches positive infinity, our cubic will approach positive infinity. That's this area and this area. So here's x equals negative infinity, x is positive infinity, and this is negative infinity, and this is positive infinity. So there's the end behavior that I was talking about in here. Also, a quick discussion on quadrants. Should be mentioned. And our particular graph, as I read from left to right, starts in quadrant 3, and as I read from left to right, ends up in quadrant 1. So, all this basic information gives us a pretty good idea that our graph should look like this. I've got a point here at -6, and I've got the end behavior over here. That's how we continue, and that's how we go with this. Now, I just need to take a second and set up a few more blank slides. And begin our quest to So here's our original function. Recall that it was, the way I like to treat these functions, okay, is as follows. The first term tells us about the basic family of polynomial functions that the graph follows, the function follows. The leading coefficient tells us how it opens up or down, and it also tells us about end behavior. The intercept tells us, okay, where a point is on the graph, and where it particularly establishes a set or a point where the graph crosses, okay, the y-axis. The middle terms, okay, the garbage, if you like, in the middle, okay, focus on this area here, and that's what we set out to try and look at this point. Okay, we have to factor. Okay, so what we do with factoring, okay, is, okay, things we have seen in our particular unit. Look at the last term. What are the factors according to the factor theorem? Plus and minus 6, plus and minus 1. Okay, and we also have, okay, plus and minus 2 and plus and minus 3 to get negative 6. So we start with, okay, systematically trying to find values of our particular factors. I'm going to just arbitrarily choose 1. Plug in, just like we've seen in the past. Hope for an occurrence of this particular function equaling 0. That's a good step. That's what we want to try and find. If it did not equal 0, we pick our next one, maybe negative 1. If a negative 1 didn't equal 0, we would systematically try and continue to try until we find this very first factor. This is the important aspect of the factor theorem. So what we can conclude from this, okay, is that x minus 1 is a factor of my original polynomial function. At this stage, I can perform long division on my original function and hope that my long division will yield a remainder of 0. That's my goal. Okay? And if that works out, that's a great first step. If you like, feel free to try synthetic division. I steer away from synthetic division, just my preference. I like the sort of the nuts and bolts and the feel of long division. So what do? Okay, it looks like we need to multiply by x squared. So x squared times x minus 1 is x to the power 3 minus x squared. Okay, subtract. That eliminates my x to the power 3 term. If I subtract a negative and a negative become a positive. That leaves me with 5x squared. I bring down my next term, and I look again at my original factor x minus 1. What do I multiply now by? Probably 5x. 5x times x minus 1. If I can get the distributive property on this, gives me a binomial 5x squared minus 5x. If I subtract again, eliminates my x squared term. That becomes a positive 5x, and x plus a positive 5x, 6x. Bring down my negative 6. Leaves me with, oh, that looks like it's going to turn out to be a remainder of 0. Times by 6. Leaves me with 6x minus 6. Remainder of 0. Good. So far, so good. So my factor of x minus 1 into my original polynomial function gave me a remaining factor of x squared plus 5x plus 6. The way I write that was a little bit interesting. I want us to get in the habit of writing this properly. This really shows full comprehension of the question. Okay. This is what our original polynomial function now starts to become. The x minus 1 factor in the front is a root, is a 0 of our function. And now I hope that I can just simply by trial and error, or by decomposition, factor this remaining polynomial. Well, I hope at this stage of the game it doesn't take us very much of an effort to realize that x squared plus 5x plus 6 has factored x plus 2 times x plus 3. Our original function is now this. Now, that's important. That's an important development here with respect to our graphing of our question. We now can, okay, remember we started with this negative 6 down here approximately. We now have end behavior in quadrant 1 tending that way. Now we have, let's change my color here, we have the negative 3, we have the negative 2, we have a positive 1, and I'm going to put that in red as well too. These roots are x equals 1, x equals negative 2, and x equals negative 3. Good. So far, so good. I think I can, at the very least now, maybe sort of sketch in my function. Let me just erase this. Okay. Now, at some point, students get a little bit picky about how high do I go up maximum, what happens down in this area. But I want to show you, okay, a confirmation of this function. Now here's our original function that I graphed. I like students to fiddle around with a graphing utility, and this is mentioned in the course materials, and I've emailed a couple of students on this. Desmos.com/calculator is a great free website that allows you to graph these functions and get a picture. Okay. This was what it turned out to be, our graph. Okay. Here's the negative 3, negative 2, and the 1. Okay. It tends this way, goes up this way. Please take some time in this unit, and certainly if you haven't already, to visit the website and build some functions in here and check these as graphs. It's always a good step at this point as you're developing a graph by hand to go and graph it with software or an app, or certainly any type of tool you can to get an idea of what this graph looks like. Now, our discussion on this maximum point here, right here. Okay, a lot of students like to not just sketch it, they like to find an actual maximum point. Here's how we find this maximum point. Notice that, the maximum, I'm going to call this a local maximum. It's just a little wee top of the hill. It falls between, it's in between, what are my roots? That negative 3 and negative 2. So sort of halfway in between, this. This is represented, as finding the value of the function at the halfway mark between negative 3 and negative 2. So I'm going to take the halfway mark between negative 3 and negative 2. That's about negative 2.5. Okay, and the value of the function at negative 2.5. Okay, I think I calculated this to be approximately, decimal will be all right. That's just simply crunching numbers into my original function, if you like. 2.5 to the power 3 plus, what was my original function? 4, 2.5 negative squared plus negative 2.5 plus minus 6. Okay. And like I said, that equals just a touch under 1/7/8, I think that is. On my function, that's right about, right in this area. That's just a quick mathematical way to find that actual point, if you like. You can do the same, okay, for the point. Okay, down at the bottom in this little area. The discussion on maximums and mins, okay, local maximums, local mins in this case is left for MHF4U, the advanced, the calculus and vectors class. Now, just to summarize and completely finish this particular unit, the whole unit, activities 1 to activity 9, we had a discussion on inequalities, just for the sake of, okay, of finishing and doing this type of question. Okay. We want to talk about this inequality. I'm just going to turn this function into this inequality. Now, remember that I previously just found this polynomial function to be this. Now, my graph gives me, okay, when this is less than 0. Okay? My original graph gives me when this is less than 0. Here's the interval, okay, that's less than 0. Okay. Everything above the x-axis is greater than 0. So if you have a graph, you can state the solution to an inequality. This would be, okay, when x is less than -3, and when x is between -2, +1. Sorry, that was is when our function, the inequality, is less than 0. A lot of students, and some students, have a difficult time with the sign chart. So let me see if I can take a few more minutes and generate a solution with the sign chart. Okay. Here's my sign chart. My roots, okay, break into intervals. And those intervals are, okay, x is less than -3. Okay. X is between -3 and -2. Okay. X is between -2 and 1. And x is greater than 1. So my first interval is here. My next interval is here. My next interval is here. And my next interval is in this area. So my sign chart, okay, I put in values into our particular function. Remember, my original function was broken down into these 3 pieces, and my original function, okay, took all of these factors, x plus 3, x plus 2. All right, so here's my sign chart. I need a value for x that's less than -3. Well, x equals -4. I need a value for x between -3 and -2. How about x equals -2.5? I need a value in this interval, -2, x between -2 and 1. The easiest one would be x equals 0. And then I need a value in my interval x is greater than 1. That would be x equals 2. All right. Let's complete my sign chart. When x equals -4, what's the value of x minus 1? When x is straight substitution, x equals -4, -4 take away 1 is a negative. I just need the sign. When x is -4, -4 plus 3 is a negative. And when x is -4, -4 plus 2 is still negative. A negative times a negative times a negative, a negative times a negative times a negative is negative. Okay? So in the interval, this interval right here, our function is negative. Okay? And didn't we, in fact, see that on my graph? Sign charts are actually a little bit fun to play with. Okay, let's do the next interval between -3 and -2. A value between -3 and -2 is, let's say, -2.5. That's that local maximum. Negative 2.5. Negative 2.5 take away 1 is negative. Negative 2.5 plus 3 is positive. Negative 2.5 plus 2 is negative. A negative times a negative times a positive is positive. So the whole product of these three factors in this particular interval is positive. Similarly, negative, positive, positive, negative times a positive is a positive. And then finally, when x equals negative 2, that's positive, positive, positive. Oh, I'm sorry, this one's positive. This one, I got my things crossed up here. This one's actually a negative. A mistake here. So that means that our intervals, where f at x equals, was my original function, are in fact, where they're negatives, here and here. That's the interval x is less than negative 3 and negative 2. Okay. X is greater than negative 2 and less than 1. And on my function graph, that's exactly what I found that to be. Keep in mind, please, that if the question is this, we would have to, since it's equal to, we would have to include those intervals. So that would simply just mean that our x minus 1, x plus 3, x plus 2, greater than 0, our intervals would be and if you like a different notation, that's this set notation, interval notation. Okay. That concludes a long video lesson on dealing with polynomial functions. For the most part, I think if you can do those ones, the x to the power of 3, the cubic ones, you'll be in good shape. You may be expected to and asked to do x to the power of 4, degree 4 polynomial. Keep in mind that degree 4 polynomials, just by way of a review, okay, so 1, 2, 3, 4, okay, that's the leading coefficient, okay, is positive. It's going to look like that. There'll be messy stuff in the middle. You do the same way. Analyze the function, factor to find the roots, and build from there on what it is you're trying to solve and find. Okay, good luck, and I hope you appreciated the review, and you have had a good work in this particular unit.
Great.